I didn't prepare slides because I had this old-fashioned notion that we should, have a discussion. And the last time they put me up here to do a discussion, I kind of lectured. So this is penance. Now, we've just seen a series of very interesting talks that have raised a lot of questions, only a few of which people got off their chests. And at least in one case, people were told to defer it till now. So now is now. And I suspect we have more than we can reasonably get through in the, is it the half hour till lunch? 1 hour. Okay. So we might be okay. We will have to see. Let's just try to do this in order and see where it leads us. I may force us to move along from time to time. But so let's start, Susan, with your talk. There were a number of interesting things you had to say, but I noticed that we basically shut up Dimitri in the middle of raising a question about your talk. So probably you should go to the mic and maybe try to address Dimitri's question, and we can take it from there.
We have to put Dimitri in the other mic so we can make sure he has the question.
Or we could just bring Dimitri a mic.
That works. Yeah, okay. Well, okay. Let me give my understanding of your comment first, and then you can correct me, and then I can give my answer. How does that sound? Okay, so you raised that I had put on the slide Lazarian and Picozzi in 2001 as the citation for this idea that structures in thin channel maps of H1 emission are dominantly velocity caustics, right? Which I am not purporting on my own, but I put that there because that's the citation that the Lazarian group uses when they are claiming that all of these structures are due to velocity caustics. Now, I understood your comment to be that that paper is about the 2-point statistics of the emission and not specifically about anything about the morphology of magnetically aligned structures or filamentary structures or anything like that. Is that what you're saying, first of all? Awesome. Okay. I agree. And my comment here is that it is the small scale structure of the channel map emission in general that is associated with the cold neutral medium phase. It is not specifically the filamentary or magnetically aligned structure, although the small scale structure does tend to be filamentary and magnetically aligned. But it's quite literally the high K, it's the high wave number end of the channel map emission in general that we show is dominantly structured by the cold neutral medium from these comparisons with the far infrared broadband emission, from these comparisons of the sodium-1 absorption structure, and various other ways of attacking this problem with completely independent data are all consistent with this idea that the CNM is preferentially small scale, it's preferentially clumpy, it's this cold, small scale component of the medium that also has a very narrow line width, which means that when you take a narrow channel map of emission, you have a greater contrast in the emission structure from this high K, preferentially small scale CNM. And that means that you also have a prediction from the multi-phase structure of the H1 that if you take a channel map over a narrower and narrower velocity range, you should see a flattening of the power spectrum due solely to this increased contribution at high K from the small, cold, clumpy stuff. And that's consistent with several different lines of investigation that are actually abjectly inconsistent with these structures being dominated or even measurably velocity caustics. And I promise you this is coming from, I'm just asking the data what things are. I have no agenda here.
Am I supposed to argue?
No,
right.
you can agree if you
Now we
want.
fight.
I will actually not even argue. So I will just go back to 2001 paper and quickly summarize what was the main point of it. And this point is overall valid, but particular conclusions is actually an interesting topic of discussion. So the point is that whenever you have a velocity slicing and you deal with a PPV cube and not three-dimensional real space cube, you have a mapping from a real space to a PPV space. And this mapping has contribution both from density effects, which whatever density is distribution of the gas, as well as velocity effects. In particular, even if you have uniform density, your mapping will still create some structures in PPV space. So 2001 paper was just studying this effect in a language of a two-point statistics, like a power spectrum or a correlation function. And actually 2004 paper was simpler than that, so we rephrased it in a simpler way. And main conclusion was that, first of all, there is a concept of a thickness of a slice, whether it is thin or whether it is thick. Thickness is determined by comparison of the velocity dispersion on that scale, or structure function of the velocity of that scale, with a separation on which you make an observation. So thickness of a slice versus variance of the velocity on that side. And if you, in a thick slice, you start averaging velocity effect out. If you are in a thin slice, velocity effects are overall largest. But the balance between velocity and density effects depend on the underlying three-dimensional spectrum of density and the velocities. So in particular, if density has a steep spectrum like velocity one, like a Kolmogorov one, then in a projection, you would be actually in a thin slice mostly measuring velocity spectrum. So, however, if density has a shallow spectrum, it has a strong contribution from the short wavelengths, like you have tiny, tiny clouds, for example. Then in the projection, you will be mostly measuring density spectrum, even in a thin slice. But the slope of the spectrum will be actually modified by velocity contribution. You will not directly measure the slope, which is three-dimensional on the line, but with the velocity a bit rescaling it does. So that's basically what 2001 paper is.
Yep.
So in that sense, fairly obvious, if you make high-density tiny clumps and spread them around, then velocity will not smear them out, right? So you'll be just picking up those clumps, even in a thin velocity channels in that sense.
That's right. That's
So
right.
so that is what I want to make clear. In that sense, attribution of a statement about morphology to 2001 paper is...
Which is not my attribution.
But it appears, goes from slide to slide. So it is a misattribution, and basically in that paper I can vouch for every word written.
But let me make clear. Sorry, go ahead.
Yep. Now you raised actually two additional arguments about why it is density one. That is, I'll postpone my discussion to just study them better, right? So,
Yeah.
for example, with absorption lines. So.
Right. Okay. Exactly. And it is also true that, for example, in the extreme case of a constant density medium, that any channel map is going to be structured purely by velocity caustics. This is a situation you can conjure in simple numerical simulations. This is especially a situation you can conjure if you translate between PPP and PPV space without any sort of thermal line broadening, which is inescapable in a physical medium. So that was, I think, one of the early things in the 2000, 2001, et cetera, papers led down a path of having these numerical simulations that way overestimated the contribution of velocity caustics, even in a simplified version of things. But more importantly, the statement in the actual data is that there's no measurable contribution of the velocity caustics to these H1 data at all, and it is absolutely not the case that in a 3 kilometer per second channel map, as was claimed in many papers from Lazarian's group, that the structures that dominate that you measure in any sort of in this rolling Hoof transform that I've used, in taking the spatial gradient, anything sensitive to the small scale spatial structure is absolutely not imprinted by velocity caustics. I mean, we can rule that out with the observations. We can, yeah.
Cajo? Yes. That's a strong statement. Numericists will take a microphone answer.
I thought you would speak something for me. But okay. So let me be fair. So first of all, I usually call LP, Lazarian Progress in 2001 as LP00. So take it as my word. So to be very honest, as of 2024, I believe that in H1 maps, they are both density and velocity structures. It's a matter of ratios. It's not about whether it is either A or either B. Whether the features on the H1 map are more velocity-like and density-like actually depends on your velocity positions. So there's a very simple argument. So suppose you throw a particular code CNN, throw it like 50 kilometers a second away from you. Would you actually call it a density feature, or if you call it a velocity feature? So from my paper in 2021, we actually showed very self-consistently, as what Susan was doing, that if you follow our analysis, the velocity fluctuations are actually larger than the density fluctuations, if you treat it correctly. But if you forget to normalize your calculations, then you will get some very interesting results suggesting that density looks more apparent. So this is my answer to your paper in 2019. Please normalize your data. Yeah, you actually write something recently.
That paper is in physical units. So it's making a measurement in physical units.
Well,
I see that you have, well, not published, but put on archive these strange things, arguing that if a measurement isn't in units that go from 0 to 1, then it's somehow not valid in some way. I'm using physical units in the paper that showed that the statements that channel map structures at 3 kilometers per second were completely velocity caustics is inconsistent with the data. But that's also not the only observational test, independent observational test that we've done from the data that exclude this velocity caustic explanation for the structure. And this is not to say that the velocity of the data doesn't affect where things end up within PPV space, right? Of course it does. It's a question of, is the channel map structure that you measure when you take its spatial gradient or any other metric, is it dominated by velocity caustics? And it's just not. And one of the other ways that we've shown this is through the sodium-1 absorption line, where what you can show is that using millions of quasars and their measurements of the sodium-1 absorption doublet, which is a tracer of cold gas, as hopefully everyone in this room has thought about the ISM knows, what you can show is that the equivalent width of the sodium-1 absorption is much more sensitive to the small-scale channel map structure than it is to the total H1 column, which is directly consistent with that being primarily colder, neutral, medium structure, and it's directly inconsistent with a strong contribution from velocity crowding to that channel map structure, because that would actually go the other way if you think about the partial saturation of the sodium-1 D1
That is actually why that goes wrong. So in your paper...
And just, sorry, just to put this here, this is Peake and Clark, 2019, as the sodium-1 work.
Papers. So the issue here is we are saying that the whole H1 feature contains both velocity and density. And the density part is being shown to have some correlations with different features. That is great. But actually that does not exclude the existence of velocity caustics. So just make very clean argument here. Are you saying that it has to be either density or either velocity?
I'm saying that you've published many papers claiming that the small-scale structure is dominated by velocity caustics. That's testable in the data and ruled out.
Well, I show you in my paper that using the exact same data in your 2015 paper, and I show you that the velocity caustics can be dominant in the channel. And the spectrum, no matter the spectrum, no matter is the fluctuations, velocity fluctuations could be dominant compared to density. But I did not say that it has to be dominant over all channels. So it's a matter of more or less.
I don't want to prolong this to the point where we lose all the audience. Can I just ask one clarifying question, either or both of you? You've made specific reference to the idea that you're making these observational claims about small-scale structures, but I don't have any intuitive feeling for what distance you're talking about.
Oh, yeah. We have our best distance constraints on the H1 data from 3D reddening measurements of the dust. So now we know the distance to nearby stars from Gaia very well, and that means that you can measure the differential reddening as a function of distance and constrain the distance to the dust, right? And from that, we know that the diffuse high galactic H1, where we're making these measurements, that medium is really no closer in any direction than about 100 parsecs, and no farther away in any direction than a few hundred parsecs. So we actually have a pretty nicely constrained range of scales.
I was actually asking about the size of the features.
Yeah. And then we're resolving this down to 4 arc-minute resolution in the Arecibo data, which if you put things 100 parsecs away is order 0.1 parsec physical resolution.
Okay, and if I were to ask how big a feature are you making these claims about?
I would say that it depends what claims you're talking
Well,
about.
I'm saying, okay, so you've made a strong case for the primacy of density structures to explain filaments. Do you mean that to apply to all filaments within the survey scale?
What I mean is that there is on the scale of about the resolution of the data or slightly larger, where you're, for example, taking a spatial gradient or whatever, the dominant emission structure at that scale is, yes, physically correlated with the density structure of the medium and preferentially the CNM in the H1. Yeah. Okay. In these narrow channel maps.
So, okay, so we're talking about features of a size, a fraction of a parsec. Or
well,
a few parsecs?
Okay, I would also say that the medium tends to be, look very filamentary. And so the width of those filaments are, maybe marginally resolved even at a resolution scale. I mean, they can get quite thin, then they're pretty elongated on the plane of the sky. But I just want to be clear that I'm making a very general statement about the small scale structure in general that is also true of the filaments, but actually does not depend on whether or not you've specifically selected for that morphology.
Okay, thank you.
Thanks.
I'm sure we could get more going here, but let's move on. We don't have to confine questions and discussion to things that have occurred to me, of course. So if anyone wants to stop and ask a question of, yes.
So this is related to Susan's talk, but I talked to her offline, but I wanted to it's really not a question for Susan, but for everybody to think about. As a plasma theorist, I want to describe the nature of the turbulence in terms of some number of dimensionless parameters that describe the conditions of the turbulence and the conditions of the plasma. And so in watching Susan's talk, it got me to thinking, if we're looking at this 21 centimeter line emission and interpreting that as directly related to either the cold neutral medium or other parts of the warm neutral medium, how well can that kind of observational data and other information be used to constrain the properties of the turbulence to determine some of those dimensionless numbers that characterize the turbulence? So, for instance, is looking at the cold neutral medium or the warm neutral medium missing some part of the turbulence? Are those coupled to the turbulent motions differently? And are there other observational ways that we can look out at the astrophysical world and constrain what is the nature of that turbulence at whatever length scales that we're able to measure? And then how can we use that to inform theoretical models that we can use to predict, for instance, the turbulent plasma heating that will occur when that turbulent energy gets down to small scales and eventually gets converted into particle energy? I'm going to actually lead a discussion on this on Friday, but I wanted to kind of pose this question now because we started out with an excellent observational talk, which I think is always a great way to start any theory conference, is ground truth with some observations, and say, what are the things we need to measure in order to better understand the turbulence and its impact on those astrophysical environments? Anybody?
Actually, I have a comment on that. Because the simulations that Mordecai showed did actually show different slopes, for example, in the growth rate, and I thought they were associated actually with different sampling, preferentially different phases of the turbulence.
We did in detail see different growth rates in different phases. That was that plot showing the entropy versus the growth rate. So, I mean, the detailed growth rate depends on the sound speed. So the hot phase, everything swirls around a whole lot faster.
And that is what makes most of the growth, right?
Yeah, although the strongest field ends up in the cold phase just because it accumulates there.
Yeah, okay. Xiao?
So yeah, I guess this is also a question I want to hear more discussion on. So when we say turbulence in the SM, there are different tracers. There's the velocity is something we want to get, but observationally it's very difficult to get clean velocity measurement to see turbulence directly. So there's a density fluctuations, magnetic fluctuations that we measure. So one point is that we know the Croucher Zeeman measurements of magnetic field shows the magnetic field strength and density are not correlated in diffuse medium. So there is something I wonder, so if the morphology of them aligned with each other, but the strengths of them are not correlated, how can we understand this kind of like a disagreement? Mordecai, you want to say something?
I wanted to say something about work being led by David Whitworth and Ralph Pudritz, which is combining a set of DCF measurements that extend into the diffuse medium, Davis-Chandrasekhar Fermi measurements, so looking at the wiggles and the polarization to derive the field strength, and looking at a whole lot of numerical models that extend down into the diffuse range. And both of those sets of data appear to show continued decline, something like perhaps consistent with B proportional to n to the 1/2 into the diffuse medium, which might be expected if it's a low beta medium, which I think we kind of think it is since Hylas and Trollin told us so. So I think the problem is that there just aren't that many low density H1 Zeeman measurements, because that's a hell of a demand on any radio telescope. Now, are DCF measurements reliable? They all come out something like 7 to 10 or more times higher than Zeeman measurements. So at least in high density regions, I have concerns about what gravity, my usual bugbear, does to a DCF assumption, because now you're dragging the whole frame of reference in. But that's a different set of questions. But I think the statement that the magnetic field density relation in the diffuse medium is flat should be perhaps taken as not yet definitive. I'll go that far.
Oh, so I also have a question for Mordecai and probably Chris first. So when we talk about the nonlinear stage of small-scale turbulent dynamo, I think it's the issue that where the saturation is, what is the peak of the magnetic energy spectrum is, if the energy is not in equipartition. I again want to mention this rotation measure spectral measurement that done by like Rayner-Beck and Harvard-Korn, and they suggest like a 200 parsec as the correlation length of the turbulent magnetic fields. So I still wonder whether this is consistent with the simulation tells that if the spectral peaks at something smaller than the driving scale of turbulence, which we believe
The
is also like a
driving scale
100 parsec in ASM.
It peaks at a wave number smaller, you mean?
No. I mean, real scale. So if
Oh,
we
okay,
say,
so the driving scale is like 70 to 100 parsecs? This pure supernova-driven turbulence has a 70 to 100 scale, a parsec driving length. Real galactic turbulence, you can trace out to, there's power increasing out to beyond a kiloparsec if you look at like H1 maps, which is probably like effectively two-ray instability. That is large-scale gravitational structure. And so relating actual kinetic driving scale to actual magnetic fields, I think one would have to be very careful about assuming that it was only being driven at the 70 parsec scale. The magnetic field that we observe is a combination of a disordered and an ordered field. I don't know that I would argue that all of the disordered field is purely driven by the small scale dynamo. Because certainly you are ordering disordered field in the large scale dynamo. And what that does in practice is it makes something like what I showed in my model, our model, that has sort of chunks of ordered field in a somewhat disordered pattern, which could play havoc with trying to interpret a rotation measure purely in terms of two components.
So 70 parsecs is the scale of this is the scale height actually, right? The density scale height.
Well, it's the scale height of maybe the cold H1, but there are multiple scale heights.
Yes.
There's the warm H1, there's the cold H1.
And so if the supernova really drive at that scale, that's quite remarkable because they are themselves so much smaller than the scale height.
They're super bubbles.
They are then superbubbles, yeah. So
Yeah.
most of the driving comes from superbubbles.
Probably.
And then the answer to your other question about the magnetic peak, that is usually a somewhat higher wave number by a factor of 5 or something, I would assume, because that's what we always find in MHD turbulence.
I also wanted just to say, based on some of Phil Hopkins' latest work, and I'm a small-scale dynamo guy. I like small-scale dynamo, but he was showing that there really was no need at all for a small-scale dynamo in his galaxy sims. You can just grab all the magnetic field you want from the environment around you and just advect it into the disk, advect it all the way down, all the way to the accretion disk. And he just showed this beautiful B is proportional to rho 2/3 through 10 orders of magnitude of scales. Now, I don't know if this is a problem for small-scale dynamo theory, or if this is just kind of the mean, it's just, this is the mean and there's still all this small-scale dynamo fluctuations. But it'd be nice to discuss this kind of extra piece of physics that many people know about.
Can I ask just a clarification? Where does that magnetic field in the environment come from?
Just all around the galaxy as the galaxy.
But where does it come from?
Yes, I get your point. But I'm talking specifically about the magnetization in the galaxy. Yeah, agreed. I mean, that's on much larger scales, right? And then you need the outer scale of the turbulence to be on larger scales again. So I think the outer scale of the turbulence is, what are we talking about when we talk about outer scale of the turbulence? Are we talking about within a particular region? We have an expanding box, we can make it larger and larger. Does that outer scale move out further and further as well? Or is there a outer scale? The outer scale?
Mordecai.
So if we're talking about an actual cosmological simulation, I think your basic statement that the field is not being generated primarily in the galaxy is probably correct, because it's we've already seen arguments, for example, from Cerrone or his competitors, Juan, is that the right name, Luca? That the seed field can be generated by Weibull instability in accretion flows, and that then can be taken by a small-scale dynamo at the kinetic scale. So these are actual PIC simulations of Weibull instability followed by many, many orders of magnitude of field growth in a kinetic model that already brings you up to, you know, a few % of equipartition, which is effectively what you're arguing. And so anything in a galaxy, no, it's not really going to be a small-scale dynamo from a seed field, because that's history. You're already working with something that's being concentrated, but that's still not equipartition. So you still need some process, large-scale dynamo, to bring you up to equipartition, and that may depend dramatically, according to Reeder and Tessier, on the depth of the potential well. You may not reach equipartition in very small galaxies.
Maybe I should ask a simple question and see who wants to offer an answer. So I've been listening to these talks about driving dynamos and supernova driving and large-scale forcing and so on. And just from a physical point of view, when I think about turbulence in galaxies, I do think about supernovae, but then there's also the question of tumor instabilities in the disk. There's the question of the accretion of material into the disk, which is uneven and comes from various preferred channels, but is intermittent to some extent. There is the MRI that people have suggested as being active in parts of the galaxy. And then I saw this lovely talk by Drummond Fielding talking, I forget the name of was it a fire simulation? Anyhow, the point was that he was trying to look at the balance between the circumgalactic material and the material in the disk, and there was all this question of, you know, trying to achieve reasonable mixing and maintain the cold material, and you're expelling some of it as hot material and so on. And the simulations were showing a tremendous amount of stirring due to Kelvin-Helmholtz instability, because the hot halo was necessarily not rotating with the cold disk. So all of these things have different length scales associated with them and different input energies. So it's not obvious to me that there is one answer, but a question on my mind is, what would you like to simulate, and is it really supernovae input that should be dominating the discussion?
So I'll just give you some numbers, which is if you actually, and I'll talk about energetics some more this afternoon, but the input energy is 2 orders of magnitude less from supernovae than it is from radiation. But of course, most of that radiation energy doesn't do anything anyway. So, and then if you actually look further down at, what is the gravitational energy input, it's much lower. So that is not significant to driving the turbulence, we think. Yeah, so we looked at that a long time ago. I was just, actually, Elliot reminded me of that paper for a different reason. So there, the field is amplified by MRI, but you can't reach realistic either magnetic field strengths or turbulent velocities, so, by about a factor of 2.
You were raising your hand back there. Yeah, I think... we need a mic so people online can...
Needed because otherwise it's not recorded. Here's the microphone.
I think the conjecture that gravity is not a major player in this thing could be sending the herd in the wrong direction. And so I would encourage everybody in this room to take a second look at, while the gravity clearly is not as large as electromagnetic and, supernovas, I think it's a strong underlying factor that has basically gone unnoticed until the UK now has almost a 400,000 pound grant that's looking at that. So, and the UK doesn't spill out 400,000 pounds without some group thinking it's a worthwhile stuff. So I thought I should at least put that on, let this room know about that.
Dmitry?
But gravity usually works from large scale to smaller scale.
Yeah, if you want to respond to that.
The battery is poor. Yes, that's fine. No, just you're right, but gravity works usually from large scale.
Me and mics are not. Oh yeah. I just wanted to say that gravity usually works from large scales to smaller scales, while supernova is one mechanism which actually takes energy from small scales and puts it back into large ones, which gravity cannot do, right?
We can do a duet together. I would sit there and say that's conventional wisdom, without a doubt. But there is basically they're looking at a fluid sphere of uniform density. And the, I'm sorry? Who's they? Weinberg, when you looked at his book in 1972, he did a lot of assumptions on that.
It's been progress since 72.
Yes. And what I'm trying to say is there's a UK grant, I think it's in the University of Surrey, but it might be Leeds, that basically they're looking at an unstable equilibrium in a fluid sphere of uniform density. That's the premise they're looking at.
Okay.
I'll just say one thing on supernova-driven turbulence as well, because I've been doing supernova-driven turbulence simulations and doing the shell-to-shell energy transfer thanks to Philip's amazing work. And what we find is that the compressor modes from the small scales, which are from the supernova detonations, transfer non-locally to the larger scales really, really quickly, and then they create a direct cascade in the incompressible modes. So for me, this really highlighted the difference between supernovas, the feedback, and the turbulence, the actual cascade that you develop in the vortical modes from the supernovas. And that goes all the way up to the gas scale height. Essentially, the supernovas do non-local transfer all the way up to the gas scale height, and then direct cascade all the way down.
I would just like to mention credit where credit is due. Åke Nordlund told me that in 1997.
So that would be the last millennium, right? Okay, we have a little bit of time left. I'm going to indulge myself for a second. Mordecai, would it be fair to say that when you simulate large-scale dynamos, they're still growing too slowly and saturating too soon?
Not sure. They haven't saturated yet. These are really expensive models. I'm not sure I would want to leap to that conclusion yet, no.
Isn't the main problem actually to produce large-scale magnetic fields? And we didn't have any talk on global simulations yet, but there are global simulations that really showed that the small-scale magnetic field easily saturates and grows. But the large-scale magnetic field is just too weak in all the simulations so far. And that
So
is
in
a
our
long-standing
case,
problem.
we're getting something like 20 or 30% large-scale field, which is actually
But we need
not
a global
unreasonable compared to the observations.
We need a global simulation for that.
Well, I mean, ultimately, yeah, you need a global simulation. But I thought the actual problem was that they didn't get enough small-scale fields, so maybe I'm confused.
Maybe to some people, before it was actually possible to see a small-scale dynamo in any simulations. I think the problem with supernova-driven turbulence is that you need so much diffusion to prevent the supernova from producing ringing. That was a technical problem so far, but I think it's not a physical problem. Whereas the lack of a large-scale dynamo may actually be maybe not exactly physical, but a semi-physical problem. It's another problem. It's not just numerics.
So as far as too slowly goes, let me just be a bit clearer. The high redshift measurements are claiming evidence for galactic fields of micro-Gauss at redshifts of a few. That's pretty early on. And if you want to do that from a small-scale dynamo, then you need much stronger fields so that the random line of sight you're sampling has random walked its way up to a stronger Faraday rotation signal. So it seems as though we're still struggling with getting things going fast enough.
But you showed a picture, Mordecai, where the green line was growing very, very quickly. Remember?
But that's very disordered field.
Yeah.
So there are certainly there are beginning to be high-resolution models of cosmological dwarfs that are growing field. And there are also models, relatively well-resolved models of Milky Way disks that, and I'm thinking in particular here of Martin Alvarez et al., the Oxford group, where they actually, you're in that group? Oh, okay. Who's now in Clark's group. And what they found was that classical cosmological models using genes refinement for their AMR badly under-resolved the dynamo, and that if you force the entire disk to resolve, you get a much better approximation to the small and large-scale dynamos. And so that paper, which is now about 2 years old, I think it was 22, is well worth looking at if you actually want to know what the structure of a galactic disk, where you're trying to resolve the dynamo, not the star formation, looks like.
So can I ask about numerics a bit again? Sorry. So I heard now twice from Mordecai and I think from you, Axel, that you needed a lot of artificial viscosity added to get the supernovae to work. So does that affect any of your lower density or other of the material? Is that a problem maybe also in this comparison that you showed between the different codes? I mean, we are usually using Riemann solvers, so we can do like shocks and stuff pretty well. There are problems with lower density material and subsonic flows, yes, and higher order schemes are probably better. But I haven't seen a real quantification of how much better that is or worse if you do either or.
It's certainly something we worry a lot about because, I mean, in a higher order code where we're resolving shocks with artificial viscosity, you can get it badly wrong. And indeed, if you go back and look at some of the sort of decade-old work that was done with the pencil code on this problem, it really wasn't resolving shocks at all, and it was giving unfortunate results. We actually spent several years just working on the viscosity in order to get a result that somewhat reproduces what you would get with a Godunov code. But now I think we're in a situation where the shocks only apply to, I mean, the shock viscosity really only affects the immediate neighborhood of the shocks. And therefore, the smooth flows are taking advantage of the high order lack of dissipation. But I agree that it required a lot of numerical tuning. And frankly, we still sometimes get crashes and have to tune some more. So I would say that that's certainly something that will continue to require attention.
I think this was a question specifically what is required to get a small-scale dynamo running. And so if we could in principle ask the question, if we take a Mach number of 5, for example, or 10, what is the minimum resolution with different codes to obtain a small-scale dynamo at the right growth rate? Is there any agreement so far?
I think a code comparison would be nice. I know it's boring and stuff, but I think it's important to do those things from time to time.
I suspect you're right, and I suspect it will be painful.
This actually would be
But that doesn't mean we shouldn't do it.
I suggest that someone creates a Uniturb 24 code comparison channel. I think there would be a lot of interest in trying to compare the numerics, at least from my end. I am creating the channel.
I'm sorry, I just want to be clear. You volunteered to create the channel, right?
No, he volunteered to do the comparison.
That would be nice with Hammer in there as well, actually. There's also a really nice paper on the archive in the last couple of months on discontinuous Galerkin methods and comparing it with a second order method for a supersonic turbulent simulation. They got a discontinuous Galerkin method, so you can have arbitrary order in your different cells. So you can do these beautifully high order simulations, but what they find is that they have to add so much artificial viscosity to keep things stable that the power spectra and structure function end up looking exactly the same between the second order method and the discontinuous Galerkin method. So, you know, supersonic stuff is hard. And I also wanted to point out one more thing. We talked a little bit at the start, Ethan, you brought this up, about the small-scale dynamo producing small-scale magnetic fields. Well, that is true for subsonic dynamos. You go into highly supersonic dynamos, which we think, you know, on volume average, ISM, maybe transonic. Mass average, certainly supersonic. They start creating large-scale fields. Large-scale fields as in coherent magnetic fields that are advected with all the shocked gas that go all the way up to the correlation scale of the turbulence. So this is something that I would call large-scale field. So we have to think about this as well. The ISM is not just this, you know, incompressible Kolmogorov turbulence. There's interesting aspects of the ISM that change the nature of small-scale dynamo.
I just want to defend myself here. As a large-scale dynamo enthusiast, I think of the Eddy scale as a small scale.
I guess my point is that these high redshift galaxies that do not have enough time to spend to build their large-scale magnetic field through a large-scale dynamo process do have enough time to produce it via a supersonic small-scale dynamo. That's my point.
I'm standing here with my small question, so technical one. I got a feeling from your plot that the saturation level for small-scale dynamo in high-resolution case kind of resolution dependent, that it was higher than a low. So are you convergent?
There's not a strong effect. I admit we haven't spent a lot of time on the saturation level, but if there's an effect, it's, you know, factors of percents, not factors of order unity are bigger. And we, you know, if you go from like 4 parsec to half parsec, which is, you know, factor of 8, you're certainly not seeing a factor of 8 change in the saturation level.
I have a question regarding the E-polarization over B-polarization excess. You found that in the Padoan et al. Simulation, this result was actually not reproduced anymore. And so this is really quite amazing. There must be, I mean, this is first of all a much, much more realistic setup in some sense, and then the outcome is much less realistic, right?
Yeah, that's a very interesting point, yes.
So this is done with Ramsey's code, and also it is using adaptive mesh. So the data that I used to compute this relevant spectra is just projection of AMR onto 1,000 cubed mesh, uniform grid. So part of it could be due to the fact that has been discussed here. The refinement went along with the Jeans length. And so some of the areas were under-refined, I think, in this simulation. So that could contribute somewhat to the issue. So there are so many different aspects that it is hard to tell. So for example, you can write down an equation that shows you the evolution of entropy. And so on the right-hand side, there will be like 5 or 6 different terms which are sources of entropy in this setting. And so when you quantify those terms, it appears that contributions from, for example, from magnetic field in models with supernovae driving and with large-scale solenoidal driving are completely different. So there is different sources of rotation in the fluid in different models, right? So we need to understand this better, I think. And it has to do with, I think, when you run supernova explosions, you have to add a lot of dissipation to keep the scheme stable. That changes your vorticity levels, and that affects turbulence at small scales dramatically, I think.
Susan, you also talked about EMP polarization. That was on only one slide. But did you find something about the spatial dependence, that there are certain locations where the E polarization can be much stronger than in other locations, for example?
We do see some variation of that, but there's not a ton of fidelity in the Planck measurements that we have right now to do the sort of really detailed environmental dependence study that you might want to do, right? We just need higher resolution, higher signal to noise observations to do that. The additional thing that we can do, though, is ask purely based on the H1 geometry what the E and B mode structure of the maps derived from those look like. And there we do, we reproduce this excess of E over B, as I was saying, at similar scales, or at the same scale as well measured in the Planck data. And to me, that's saying that, the physical geometrical interpretation of this that we should have in our minds is also very intuitive, right? You think about like a filamentary structure. You think about some density structure that's elongated. If that elongation is parallel or actually perpendicular to the let's just say parallel. If it's parallel to the magnetic field, you will first of all have this correlation between the total intensity and the parity even component of the polarization. If it is parallel to the field, you'll also have this excess contribution to the emission from that structure in the E mode component over the B mode component. And then in more detail, you should expect that the detailed geometry of that thing quantitatively translates to a different E to B ratio, for example. And so one of the things that my grad student George Halal has done is build something where the morphological quantification of the H1 structure is flexible, so you can tune your algorithm to be sensitive to longer and skinnier, shorter and fatter things, etc. And then ask how that adapts to the EMB structure, and what is best fit by observations from Planck or from BICEP or these other dust polarization experiments. I think it'd be interesting to do something similar in the simulations. And I would also expect that in higher density regions of the ISM, where you start to have the influence of gravity, for example, self-gravity of your structures being more important. I would expect that just as people have shown with sort of bespoke algorithms that you lose this correlation between the filamentary orientation and the magnetic field orientation, and you even move to that being perpendicular, I would expect that to translate in E and B modes to a loss of the excess, actually, to driving the EE to BB ratio closer to 1, which I think, if I'm connecting the dots between your various simulations correctly and remembering which one's which, is sort of borne out both in the different simulations and then also in when you change the relative orientation, right? You get closer to 1 when you project along the magnetic field axis, is that right? Cool, so that's consistent.
Yes, that's correct. So let me just bring one very, everybody knows this, of course. If we work with power spectra and we want to identify some structures in real space, right? It's a dangerous experiment because completely different structures can produce the same spectra. So we need to know our limits when we dream about filaments and things around them, right? Because what we know from Planck is essentially power spectra. So when we have instruments with power sufficient to produce higher order statistics, that will be an interesting game. But for now, I think we don't want to go too far from what we know, right?
I agree, yeah. So we should be saying, consistent with, but there are many different ways to produce the same power spectrum.
I was, just quickly, Susan, could it be that that there is that you don't see the peaks in the Planck observations too well? Are there detector limits that actually prevent you from getting the peaks of the distribution in intensity and polarization? So that would explain why he can only reproduce the observed data if he clips.
I have a naive question to Alexei. Yes, when you use the supernovae as a driving source of the turbulence, you do see that it doesn't fit the Planck spectrum, right? And this could be essentially due to the scales, because at Planck scales, perhaps the injection by supernovae is too small, so that and then it comes the question: what might be the real driving sources of turbulence at those scales? So can we argue that might be superbubbles, or as a product of several supernovae, or what else? I mean, winds, the Galact wind itself. Can you comment on this?
In this simulation, the integral scale of turbulence is about 70 parsecs, I think. And so, but there is no other source of energy coming from the larger scale. And so that's why I think the peak in the asymmetry ratio is cut, basically. On small scales, it is cut by dissipation, numerical dissipation, which is high in this simulation, I think. And on large scales, there is no source which we have in the ISM. And there was a discussion about whether gravity or supernovae, what is more important, tumuli, something else. I think this year in August, there will be 75th anniversary of the conference in Paris, where people started to think about this, because there were first observations of interstellar clouds discussed. And there were two persons claiming that everything is turbulent on the galactic scale. So one of them was von Weizsäcker, the other one was Heisenberg. But because it was in post-war Europe, there was a big conflict, not conflict really, but the discussion got a little bit politicized, which we cannot do here, right? And so actually some people started to talk that no, it's impossible that turbulence is large scale and coming from galactic disk, for example, right? It should be smaller scales only. And so I think we are still here at the same point, basically, right? 75 years later, we are still, we don't still know where the energy comes from.
Two comments. I mean, first of all, I actually just throw one paper on Slack. The paper is published. Okay. I actually want to follow up what Alexei and Monica was following up. So, from my understanding, media simulations are usually being driven, compressively in larger scales. Chango game, for instance, they do a lot of that. But it doesn't match with, whatever is being shown in our, simulations. I would like to at least know a little bit more, because if you think of supernova and bubble, something like that, they're likely to be compressive, right? Yeah. If you want to comment a little bit more on that.
I've just been reminded that we're out of time.
One question doesn't take that much, I think.
Fair, but then we have to call it quits.
Yeah.